So we have a question which says that thick wall tube. So the moment we see a tube, it means we are referring to cylindrical tubes, right? So cylindrical geometry of heat transfer. Tube of stainless steel with 20. So the tube alone gives us an inner and then an outer, right? Because when you have a pipe, it should have inner radius and then outer radius with 20 millimeter inner diameter. If this is the center, from this portion to this portion is 20 millimeters and 40 millimeters outer diameter. So now from this portion to this portion, 40 millimeters. It's covered with a 30 millimeter layer of asbestos insulation. So we are covering this with a 30 millimeters. So from here to here is our 30 millimeters. If the inside wall temperature of the pipe is maintained at 600 degrees Celsius, now here is 600, T1. Let's call here T2 and then here to be T3. So now T1 is 600, T2 we don't know, and then T3. The outside insulation is 1000, right? So 1000 degrees Celsius. And we are given the K of the asbestos to be 0.2 watts per meter degree Celsius. Now we are supposed to find the heat loss per meter of length. So now to find the heat loss, we understand that the heat moved from here to here will be the same as from here to here and then the same as from here to if there's any fluid. So if you want to find the heat loss, you can choose each portion we want to use. But then we have to look at the temperature. We are constrained with the temperature. Right? If you know the temperature T1 and then T3, then we can use that. But then if you also know T2 and then T3, we can also use that alone. But because you don't have information on the T2, then we are restricted to use the T1 and then the T3. So K is equal to change in T overall all over summation of resistances. Right. So now we are using the overall one because we have T1 and then we have T3. And then from the look of the diagram, T3 is at a higher temperature than T1. So the temperature drop will be from, or the heat transfer will be from the outside insulation to the inner, right? So 1000, sorry. What we derived was actually 2 pi L, right? So 2 pi L multiplying T3 minus T1 all over, right? So because it's mainly by conduction, so from here to here will be by conduction, and from here to the inner will also be by conduction. So length, and then because we are moving from 1000 to the 600, so you have to follow that same approach. Right? You can use it the other way around, but we'll be getting negative. So let's try that one and see. So let's say we are rather moving from T1 to T3, right? So we are moving in this direction. From the inner to the outer is by conduction, right? And that will be going to be ln R2 over R1 all over the key of this steel, because that is our steel pipe. So this is our steel and this is our asbestos, which is our insulation, plus. So we are going to move from here to here, right? Because you moved from here, there is no fluid here, so you're not considering any convection. So just from T1 to T2 and then T2 to T3. So that will also be by conduction, which is ln R3 over R2 all over K of asbestos. So let's find out R1, R2, and then R3. R1 will just be D1 over 2, right? So 20 millimeters over 2. Because we used radius in deriving this formula. And then we're given diameters, right? So our radius is 10 millimeters. R1 is 10 millimeters. R2 will now be outer diameter all over 2, and that will give us 40 millimeters over 2, and this is 20 millimeters. R3 wasn't given explicitly, but then they gave us the layer thickness to be 30 millimeters. Now if you want from this portion to this portion, it's going to be 30 plus from here to here. And then from here to here is our R2, right? So R3 becomes 30 plus R2, which is 30 plus 20. And that would be 50 millimeters. So you just have to substitute everything here. Now realize that we weren't given the thermal conductivity of the steel, right? So we can just assume it to be 0 because we weren't given. And then we'll definitely need it to solve it. So that means the heat loss from the steel pipe was very negligible, right? So our K will now be 2 pi L T3 minus T1. If this is 0, then the whole of this becomes 0 all over 0 plus ln R3 over R2 all over KE. So Q is equal to 2 multiplying 3.142. We want to find the heat per length, so we can divide by length and then by length. So we have Q over L is equal to 2 multiplying 3.142 multiplying 1000 minus 600 all over length. So our R3 is 50. I'm leaving it in millimeters because it's a ratio, so the units will cancel out. All over R2 was also 20. So if they are both in millimeters, they cancel out. All over the K of the aspect also 0.2. So we get 2 times 3.142 times 1000 minus 600. And that would be 2513.6 all over. So ln 50 divided by 20 all over 0.2 give us 4.581, and that would be 2513.6 divided by 4.581. We are getting 548.65 watts per meter. So now the heat loss per length is 548.65 watts per meter. Yes. So that becomes our final answer.